Hi, I'm Hannes, and today we'll have Emanuele Rossi from Twitter talking about the unreasonable effectiveness of feature propagation for using GNNs with missing node features. And if you want to join this reading group sessions yourself, you will find all the information in the description.
Yeah, so my name is Emanuele, but as I was just saying, kind of my friends call me Emma. And I work at Twitter. I've been there for almost 3 years, and mainly doing research on graph neural networks, as well as some more applied work. So basically applying these methods on real world problems we face at Twitter. And at the same time, I'm also doing my PhD with Michael Bronstein, which was also Twitter, and the PhD is in collaboration with, is with Imperial College. And today I will be talking about one of our recent works about dealing with missing or partially missing node features in a graph, and now we can learn with this type of data, which is kind of actually almost always present in the real world.
All right.
Should I get going?
Yeah, let's go. And to everyone else, feel free to raise your hand maybe, or just ask questions. We want to have a nice discussion. All right.
Yeah, definitely. Yeah, love to have a more interactive presentation. And yeah, this work has been done in collaboration with colleagues at Twitter, as well as also some collaborators at Oxford. And it's basically work from late 2021. So I'd like to start with some motivation. Basically, more generally about graphs. We probably, there's not much need to this audience, but we'll go through that quickly, but more particularly around missing node features. So, probably you all know that networks are kind of everywhere in the real world, and graphs are a great mathematical tool to model them. A few examples are social networks, which is kind of what we deal with a lot at Twitter, molecules, and very interesting applications from chemistry. So you have nodes, atoms, and edges or bonds. Then you have brain functional networks, where nodes can represent different parts of the brain, and edges basically encode when two areas of the brain kind of are active at the same time. And another example is protein interaction networks, where you basically have things as nodes, and the edges represent when two proteins kind of at the same time and inside of a cell. And we have a lot of graphs, and we also have kind of different types of tasks that we can do on graphs. So we can do graph classification, which basically means we're interested in predicting a single quantity for the whole graph. And this, in this slide, I'm going to talk about classification, but basically everything can be thought also as regression. Similarly, in this case, we have a molecule when we want to classify into whether it's drug-like, so it looks like something that can be used as a drug or not. Another one is node classification, when we do make node-wise prediction, so predict a label, a class for each node. This example, we have a social network, and we know for some users whether they are omnivore or vegetarian, and we would like to maybe predict this label for other users. And the third type of task is link prediction. A clear example is, again, social networks. We observe some edges, but there probably are some edges that should actually be there but are not observed, right? So this is what we could predict, and then recommend people, maybe you should follow this other person because you could be interested in them. So you also know that kind of now graph neural networks are the de facto tool to solve all these tasks on graphs. And there are, we can look at them through two different point of views. So one, which is usually called convolutional, and it's basically here I'm showing the equation of the original GCN paper from Kipfer and Welling. And I think, as you know, we update the node features based on the previous node features and the adjacency matrix. which we represent here in yellow. And what is interesting about the diffusion matrix is that it's a sparse matrix. So we're basically diffusing these node features in the graph. And we also have some weights, learnable weights, W. And basically the first layer, this age, are the original node features. So this is kind of some information, raw information that we have about the users or whatever our node represents. Another kind of viewpoint is that of message passing GNN, where we think about each layer of GNN working by propagating messages in the graph between neighbors. So here, if we take neighbor I, is gonna receive messages from all its neighbors. And here we show in particular one message in yellow from the neighbor J. And then I will have to aggregate all these messages and combine them together with its previous representation into a new representation for I itself. And again, the original representation for the node I is this input feature vector. So, I mean, these are two different viewpoints, but as you can see, basically the last line, the last equation in both cases is the same. So we really need this basically feature matrix X, right? So I'm calling this the GNN's unspoken assumption, is that we really require a fully served feature matrix. So basically we want this. We want this matrix where we have basically each row represent the features of a node, and we basically observe all these entries. However, in the real world, I would say really most of the times what we have is something more like this on the right, where some entries are observed, some entries are not observed, different entries are observed for different nodes. Some nodes, we may not observe any feature, right? But we still may want to do our usual graph tasks on them. So to go into a more specific example, we can think of user demographics. Let's take age in a social network. So for instance, probably age, you don't know that for all users. So at Twitter, we don't know the age of all users. And so your graph, something like this, right? You have your social graph, which connects user, and you only observe this age quantity for some of them. Other examples of graphs with missing features could be co-purchase networks, where nodes are products and links are when they are both together, where you have maybe features for one product, for a product only when there is a description associated for that product, and that is the case. When you think about features representing the content that a user generates, these are going to be present only for the most active users. If you think about Twitter, actually most users don't really generate content; they're mainly consumers, right? But more in generally, also with the big rising awareness that there is around digital privacy, more and more data will only be available upon user consent, and so you may observe features only for the users, right? Be kind of become more and more widespread. So what we're interested in, kind of our research question is, can we still learn on graphs when we have missing node features? So the goal is to solve a downstream task, such as node classification. It could be also link prediction or graph classification. In our paper, we focused on node classification, but for the experiments, the method is quite general. So basically, you have the features observed on only some nodes, and always here for the examples, I'm going to show always only one feature per node for simplicity. But what we're talking about generalized is always to multidimensional feature vectors. And we also observe the labels for some nodes. So this is the standard semi-supervised node classification task. And the goal is only to classify all nodes. So we're not, in this case, interested in reconstructing the features themselves or how good the reconstruction is. That's kind of another problem. But what we're interested in here is only the performance on the final stream task, for instance, node classification. And this is also what differentiates this work from classical feature imputation and matrix completion, where instead the goal is just to reconstruct the missing values, missing features.
Yeah, are there like the standard methods for learning on graphs with the missing node features? Are those ones that first try to reconstruct the node features and then use them in a normal GNN, or are there the approaches different as well?
Yeah, I would say, to be honest, like there are no standard ways, because quite surprisingly, is a problem that has been barely touched. I think in the literature, I think what people would have done clearly has been faced before in practice. I think, you know, what people have been done, and we'll see, you know, these are some of our baselines, are standard imputation methods. So I'm going to take the mean for these features, or you know, standard imputation methods, and then you run a standard GNN, right? This would be kind of the easiest way to deal with this problem. You know, that you can think of is just filling the missing features with, you know, 0. Not super principled, probably in some cases it doesn't make much sense, but it's kind of a very simple baseline that we can try. Another one is similar, you know, thinking is, you know, just filling with random numbers, something that makes a little bit more sense. So at least you're using information about the data, is just taking the mean of that feature over the whole graph. So in this case, the mean is 37. So we just fill everybody's feature if it's missing with 37. Something a bit more clever, which uses both the data and the graph, is just taking the mean over the neighbors for each node. So for instance, here, this node here on the left has 2 neighbors with the feature, with an observed feature. So, and they have 29 and 13. So basically the mean of that is, you know, approximated by 23. And however, you already see kind of one problem with this approach is that if a node doesn't have any neighbor for which we observe the feature, then it's not even defined what this approach should do. So we can, you know, resort to just using 0 or any other method, right? But it's already, you know, it's curious, facing some issues. And this is what happens to this top left node. There is also, as I was saying, this problem is largely unexplored. However, there were 2 previous papers that kind of looked at this problem of learning with missing node features. One is called, the method was called GCN-MF, which the idea is to represent the missing data with a Gaussian mixture model, and basically compute the expected activation for a first GCN layer when modeling the features in this way. And then every layer from the second onward is just a standard GCN. Another one is called PA-GNN, so basically partial GNN, which does a partial GCN-like message passing, where again, in the first layer, only the observed features are propagated in the graph, whereas the features which are not observed are not propagated. However, these methods kind of face two problems. The first one is that they really suffer, and we'll see the experimental results later, but they suffer in regimes of high rates of missing features. Think of, you know, more than 90% missing features. We're gonna have experiments up to 99%. And also the other issue is that they do not really scale to large graphs, which is something we're obviously very interested in Twitter. So we'll kind of try to provide solutions for these 2 problems. So just a glimpse of our idea, and the main idea is quite simple. So it's basically to do a reconstruction of the features, which promotes smoothness on the graph. The smoothness of us, and this is usually called homophily assumption in graph neural networks, right? And by homophily or smoothness of a signal, we mean that we expect 2 neighbors to share similar values of a given feature or of a given label. Like, so 2 neighbors are more likely to have a similar value than 2 random nodes. So in this case, the signal would be smooth. And smoothness is measured through Dirichlet energy in the case of continuous features. And the animation here just showing basically what we see at the end, so what our method does. And again, if you look at the final result, the value which start not at 0 are the one where we observe the feature, and you'll notice that the others are reconstructed in a way that the signal tends to be smooth on the graph. And what is interesting is that this is kind of the same assumption that most GNNs make, such as GCN, GAT, GraphSage, etc. They are kind of, by the fact that they are diffusing on the graph, they tend to smooth the signal, and basically they've been shown to work well and to also make this when this homophilia assumption holds, which is very often the case in most benchmark we're working with. Now there is a lot of work also in heterophily, and is also something we will touch on at the end as well. But we think this approach works well in conjunction with GNNs, because they kind of make the same assumption of the homophily smoothness of the signal. So let's introduce some notation first. So we start with a feature vector. So again, only one-dimensional features for simplicity. However, this kind of generalized to multidimensional vectors. So we have as always, you have a feature vector X. In this case, however, we group the features such that the first K nodes are the ones for which we observe the features, and the bottom U nodes are the ones for which we don't observe the features. And in this vector, you can at the start you can set their value to anything, right? Because we don't really know. We'll see in a second what we will do. Also, the adjacency matrix, if you do the splitting of the nodes, the adjacency matrix also kind of can be divided in the same way. For instance, if we take the bottom right, this is going to be just a subgraph between nodes with features missing. But in general, you have these 4 blocks of the adjacency matrix, right? All the graph between nodes where you observe the features, graph between nodes where you don't observe the features, and the other 2 pieces are the graph between basically nodes that you observe the feature and nodes that you don't observe the features. Then we have the degree matrix, as always, is a diagonal matrix where each entry is the number of neighbors for each node. The normalized adjacency, we're going to take the symmetrically normalized adjacency. So this is what is used in GCN as well. So it's basically just a normalization of the standard adjacency matrix, and also the Laplacian, which is just identity minus the normalized adjacency matrix. So this will be the normalized Laplacian. So as I was saying, our idea is to promote smoothness, and we measure smoothness by the Dirichlet energy. So the Dirichlet energy is illustrated in this first equation, and it's basically the quadratic form of the Laplacian, but the definition on the right is actually a lot more intuitive. So if you look at what this is doing, this is just basically measuring for each node the average difference between the signal on the node and the signal on its neighbors, and taking the square. So by this definition, you can immediately see that if the Dirichlet energy is low, it means that neighbors have similar values for the signal, and if the Dirichlet energy is high, it means the difference between neighbors is very high. So if the Dirichlet energy is 0, it means that the signal is basically all neighbors have the same value for the signal. So we're now interested, since we're interested in promoting smoothness, we want to minimize this Dirichlet energy. So this would be kind of the second line here. And however, we only control a part of our vector of features, right? We want to modify only XU, which again, if we go back here, is the part for the unknown features, because the other features are known, so we're not going to touch them. So we want to optimize over the unknown features and minimize the Dirichlet energy optimizing over them. This is a closed form solution, which is what you have in line 3. And however, it's a bit complicated, but it's not important to go into the details. What is important is that this closed form solution involves an inversion of a sub-Laplacian, which in the worst case could be basically almost the whole Laplacian. inverting this matrix is like very expensive, right? So it's quadratic in the number of nodes, which is definitely not scalable. So we want to find an alternative solution to this problem, which is a lot more scalable. And there exists a solution which is a lot more scalable, and that involves looking at the gradient flow. And if we take the gradient flow, so we know that the gradient flow is basically a continuous equation which indicates the trajectory of x in order to minimize the given function, in this case, the Dirichlet energy. So, and the gradient flow is just defined as the minus the gradient. So if we take the gradient of the Dirichlet energy, it's equal to the Laplacian times the signal x. So the gradient flow of x, so the derivative of x, is going to be equal just to minus this, so minus the Laplacian times x. And this gradient flow, as I was saying, is a solution that tells us how to change x to minimize our Dirichlet energy. So if we are able to solve this differential equation, its solution, as t goes to infinity, will be the x that minimizes the Dirichlet energy. So now our problem changed to just solving this differential equation.
Wait, but here we're talking about xu in the end, actually, right? We don't want to look at the whole.
Yeah, good question. So here, I forgot to mention, but it's basically the second subtitle here. So for simplicity, we're just going to look at the case without thinking about splitting x, just in the general case. And then the next slide, we're going to look at when you actually only want to optimize over a subset of the features. So this is the general case first for simplicity. Thanks for reminding me.
Can you repeat? Sorry, can you repeat?
No worries.
The Lx of, like, we're taking the gradient of L. What is L?
So L is our Dirichlet energy, that basically this thing here, which again is just a measure of smoothness of the signal. So if L is large, it means the signal is not very smooth. If L is small, the signal is smoother. So we want to minimize L. Yeah,
now we treat kind of the Dirichlet energy as a loss, like we want low Dirichlet.
Basically, yes.
And then we take the gradient with respect to our input features and change the input features such that the loss or the Dirichlet energy becomes smaller. Okay.
Exactly, yes. Exactly. So what we'll end up doing is basically doing gradient descent of the Dirichlet energy, basically by changing x. So that's exactly what we'll be doing. And that is obtained when you want to solve this differential equation, which is the gradient flow. And we can solve it using any discretization method. The simplest one is the Euler discretization, where you basically say the next value for x is just going to be the current value, and plus the gradient times the step size. Step size, we just take 1 in this case. So just became plus the gradient, which we just computed, or plus the gradient flow, sorry, which we just computed in the step above. So to solve this equation, we will just need to repeat these steps because we want x kind of going to t going to infinity. And we just take this step over and over again. And if we factorize this, so this is, let's say, x at time t minus the Laplacian times x at time t. So we can factor out the x on the right, and we get the identity minus the Laplacian.
Oh, wait,
and
sorry, isn't the delta that you're drawing here, isn't that dependent on the time step we're in? Because
the delta is just the Laplacian, right? So it's just the graph, basically depends on the graph structure.
Wait, what am I getting wrong here? Like, we're taking yeah, okay, no, makes sense. The gradient that we're taking does not depend on the x. Okay.
I mean, it depends on the x.
It depends on the x, but we can factor out this
Exactly.
single a wiggle, and that's all we need to do.
Yeah, exactly. So basically here we get I minus delta, which is basically the definition of the normalized adjacency if you kind of shuffle things around. So if we look at this, if we take a step back, this is basically telling us that our, when performing, as I was saying, gradient descent of the Dirichlet energy, we can solve this by iteratively computing the next x as just diffusion of the current x, because we're multiplying x by the normalized adjacency, right? So we're just performing diffusion. This is basically what you would have in a GNN if you take out the weights and if you take out the linearity. So some sort of simplified graph convolutional network. However, you would need to keep doing this forever. Now, we know that in these
but we are sort of lucky, right, that this happens. And it could have happened, like, it's just because we're using this Dirichlet energy, which we assume is a nice function to minimize, to update our features or to smooth them out. And just because we're using the Dirichlet energy, or maybe it's also defined from that direction, just because of that, it happens to be the case that we can basically just take a power of the normalized adjacency matrix or a power of some matrix, and it just ends up being a diffusion, right?
Yeah, of course. I mean, it's as always, like in maths, you need to make some assumptions to get to nice results, right? I mean, here the assumption is not even like it's basically what all GNNs are making, right? So of course, if you take like a random, any other function, you're not going to get to this. So this is deeply connected to the Dirichlet energy, right? So here is saying that diffusion. I mean, he's not saying something, something new. It's just saying that diffusion, it's kind of smoothing things on the graph, right? It's just kind of reframed in a different way.
Yeah, but I just don't understand why we're saying we're minimizing the Dirichlet energy to diffuse our graph instead of just saying, yeah, we diffuse our graph with the normalized adjacency matrix.
Well, because to start with, you don't know what you want. Like, your goal is not to diffuse. Your goal is to minimize the Dirichlet energy.
Why is that?
Because basically you want to you're making an assumption of homophily, of smoothness on the graph, right?
But that is,
and then you derive that to achieve this, you need to do diffusion.
Okay, so we can't say that diffusion, or that we just know that diffusion is a smoothing out of the features.
Well, you know, because people have done this going this way first.
Okay.
Otherwise, you wouldn't know, right?
Okay.
But I mean, this is kind of obvious. But like, if you go to the case of missing features,
okay,
then basically it becomes less obvious.
There, this framework
but still,
will help us.
Yeah, but I still think it still makes sense in this case that you start from like a principled objective, and then you derive the method, right? You don't start from the method. I mean, you can also start from the method and then try to understand what the method is doing, but this is kind of giving a derivation.
Yeah.
So if we now look at the case of if you do this same derivation, but keeping the known features fixed, so the full derivation is in our paper, but the end result is this, where basically now, instead of just having the standard adjacency matrix here, we have a slightly different matrix, where actually it turns out that is still kind of very similar, because the bottom U rows are identical. What changes is the top K rows, which are the ones that affect the known features. So the nodes with known features. So the idea is that the known features, we want to leave them unchanged because they are known, so we don't need to touch them, right? These are kind of ground truth. And we only want to change the bottom features. So this is what these two submatrices are doing. So the left one is basically diffusing from known features to unknown features. And the right one is diffusing among unknown features, which at the first step is not going to do anything because the unknown features their values are kind of random. But as the unknown features, get information from the known features, then also diffusion among them is kind of very meaningful. So this is what you derive by doing the previous derivation by fixing this constraint, which again, I mean, it's clearly is intuitive, but I think it's a good thing that is intuitive. But I think it's not that easy to just say, okay, this is probably just starting from here and saying this is what actually makes the most sense. But if you do the derivation, this is what you get, and then it kind of makes sense. When you think about it, it makes sense, which I think is kind of a plus.
And what are the features in the beginning?
Yeah, I'm gonna talk about that in the next slide.
Okay. Yeah.
So here on the right, it's some pseudocode of the algorithm of this feature propagation algorithm to reconstruct the missing features. And so we have a feature vector X. So we show in the paper that the initial values for the missing features, they do not matter, in the sense that the result at convergence of this algorithm is independent of the original value. And this because if you think about what we're doing, at every step, we are kind of keeping the known features fixed. So we are kind of always reinjecting this knowledge. And so as you keep doing that, the values that you initially chose for the unknown features don't really matter. So the input is this feature vector X and your diffusion matrix, A tilde. And what we saw before, so this matrix that we saw before, this turns out to be identical. And I think it's a bit more intuitive to think it in this way of just performing normal diffusion. So you multiply by the standard normalized adjacency. And then at each step, you reset the known features. So you kind of take the ground truth and you put it back in. And this actually is what makes the whole difference, right? Because if we think about unconstrained diffusion, so if we go back here, I mean, we all know, or I mean, it's quite well known that if you keep doing this forever, this is going to result in oversmoothing, right? So, doing diffusion forever, your final feature vector is going to be almost meaningless. And this is what is commonly referred to as oversmoothing. However, here, since we're reinjecting, yeah.
I think what you're saying right now, we can nicely relate it to Guo Li's question. Could you explain more how is the final solution different from applying the mean aggregation iteratively?
Yeah, so if you do the mean aggregation iteratively, it depends what you refer to mean aggregation. If you just do mean aggregation, would basically be something like this with a slightly different matrix, right? Because it wouldn't be exactly A tilde, it would just be a different normalization. That would be mean aggregation iteratively. And the main difference here is actually in the fact that after each step, you want to reset the features. So mean aggregation, you could also use it here, right? Again, if you change the diffusion matrix. That is not like a major difference. The main difference is actually at each step, resetting the known features. And this is what prevents oversmoothing, because you are always kind of reinjecting this ground truth knowledge. And so the solution of convergence in this case is actually meaningful. compared to all other GNNs where we don't want to go we don't want to have too many layers unless you have residuals, unless you do some trick because they don't really work. In this case, is actually the solution at convergence is what you want. And in practice, we find like 20, 30, 40 iterations. 40 iterations work well for all data sets we experiment with. So 40 times kind of these 3 lines. And as if you look at this algorithm, it's basically very, very simple and very efficient. So it just consists of a sparse to dense matrix multiplication. And so it basically is super scalable, which is one of the objectives we started with. So I see a raised hand by Dominic.
Okay, let's get into that first. Or no, maybe let's first say this kind of what you just said. You do 40 iterations, right? And so in the chat, we also had the question, how fast do the values converge? After 40 iterations, do you have full convergence, so to say? Do you have any notion of that?
Yeah. So basically, after 40 iterations, that was basically enough for all data sets. We didn't do too much investigation into exactly how many you need. It also depends clearly, the more missing features you have, the more you will need. But the thing is that these operations are so fast and the steps are not that much that it didn't really matter.
Okay, then let's go with Dom's question or point.
I just want to go back to the comment about like how does it differ from doing simple mean aggregation repeatedly. And in some sense, like you could also re-inject the known values even if you do mean aggregation repeatedly. So from my point of view, I think it would be very similar because when we look at the solution to the diffusion equation, well, the solution to the diffusion equation and the solution and the random walk that would be equivalent of doing multiple mean aggregation, they actually converge to the same thing.
Wait, so we said it's the same, right? Like it's the same, but we just reset the features every time after each aggregation step. Like
it's practically the same. So basically, like here, it's kind of you're looking at kind of an interpolation between missing nodes. Like if we take if we look, for example, at a given curve in one dimension, you have missing points into a certain part of the space of the curve, while you try to interpolate as smoothly as possible in between the curve. So this is kind of the strategy works pretty well as long as we're in a space where the curves are smooth enough. But yeah, I think I'm just repeating what you just discussed earlier.
Yeah, no, exactly. Just a different diffusion matrix. So basically replacing this A tilde by different normalization of the adjacency matrix. But the ideas are the same, basically.
Okay.
Should I go on?
No, let's maybe get into this, like the Dirichlet energy.
Sure.
There was some interest in that. A geometric interpretation of Dirichlet energy on graphs. Like, because we kind of want to think in some physics direction here. Do we have any connections there?
Probably there is.
Okay.
To be honest, the way I think about Dirichlet energy is literally just kind of computing some sort of average difference, square difference between neighbors. I think that kind of is what gives the best intuition, to be honest, at least for me.
Yeah, and then does the method to reconstruct the features depend on the GNN task?
So in this case, as basically you can see here, this is task independent, so it's kind of agnostic of the final task. which is, probably is not optimal for a given task. And we also, to be honest, when I started this project, the idea was to have a method that was task dependent, so kind of learnable and an end-to-end way with the final model. However, when we kind of tried this method first, I was actually surprised by how well it worked, and the fact that it was kind of principled, and in the end, it's kind of super scalable and simple. So initially, we were not thinking of, this was not like the final idea, but at the end, it worked so well, and it has so many benefits that we actually preferred these to other more complex methods.
Also, okay. Yeah, sorry. Did you want to say something else there?
No.
Okay. Then Payam asks, what does resetting the features mean? The known features should not even change because of the structure of A tilde, right? But yeah, no, the A tilde is just the original normalized adjacency matrix, not this modified one that you had on the previous slide, right?
Yeah, exactly. So these are two ways. So you can either multiply by this matrix, which is a modified adjacency, and this does the whole job, or you can, I think it's a bit more intuitive to just use the normal adjacency matrix, so without the I and the 0, but just the original one, for the diffusion, and then reset. But the two things are equivalent.
Okay, yeah, then that maybe one more question real quick. Would you have some ideas of looking at different energy, or have you ever considered looking at different functions than the Dirichlet energy?
Yeah, we did a little bit, but the thing is that, you can do many things. There's also some work that we're doing now, but the Dirichlet energy has like the big advantage of kind of being much easier to analyze than other energies, and also kind of being very well in line with what GNNs have been doing. So they kind of go hand in hand together. So it's also something that I'm going to show later. So at the end, we kind of stuck with it.
All right, one more quick question by Karim.
Yes. I have basically a more, I want to take a small step back. In general, why is the homophilia assumption a good assumption? Because like I come from a little bit from molecule prediction and stuff like that, where it's, at least for me, not directly intuitive that the features should be smooth. And do you have, so you just explained that in the end it turned out that that was a pretty good method. Do you have any explanation why in advance, or why that made sense that it's a good method?
Can I first ask if you actually use this method on molecules in the end, or is it good for molecules?
I don't know, because we all evaluated on not classification.
Okay.
So two things. So first of all, like all assumptions is an assumption, so it's not gonna apply everywhere.
Sure.
Second, I think rather very often, even though the features may not be super smooth, it turns out that the key point is that you're using this method in conjunction with GNNs. So we know that if you take kind of most GNNs, so such as GCN, GAP, etc., they will do kind of smoothing themselves. And so we know that these methods are only looking at the low frequency of the signal. So if you look at the signal in a spectral domain, they will look at only the low frequencies, right? So the smooth part. And so what we're doing here is basically reconstructing only the smooth part of the signal. So it may not be the best reconstruction, right, for the signal itself, but it's only reconstructing the information that would be used by a GCN or a GAP anyway. So there is no point in reconstructing, the signal perfectly if GCN is going to do smoothing anyway and lose, these high frequencies as well. So it has to be thought of something that works well in conjunction with this method. It's not going to work in all scenarios, as well as these methods don't work in all scenarios. And in the end, we're going to show a limitation. So if you take a heterophilic data set, the current method doesn't work, and is actually probably one of the most interesting extensions we're thinking about right now.
I see, but I'm really not an expert. But is that the case that the high frequency features in the input are just lost when applying a GNN or NN on a message passing network? They are integrated, right? It's just that in the end, there's not much left, but they are used in the beginning of the convolution. So do I get that?
I mean, they're used, but they are, by the definition of the model, they are kind of lost, you know, they're not used in the final prediction. Like they're used in the sense that, you know, the input contains them, but then if you do the smoothing that as, you know, most GNNs do, then you kind of lose them, right? So there is no point in having them.
They could be embedded, right?
Sorry?
Can you not embed them? Because like the information is obviously totally embedded in the end anyways. Can you not embed high frequency information in the lower dimension or lower frequency?
I'm not sure what you mean by embed high frequency.
So through message passing, I'm not quite getting how the information is lost or not used at all if it has
if you think about
the message passing. Yeah.
If we think about GCN, it's basically a weighted mean of your neighbor features. So if you do a weighted mean, this is gonna basically smooth out the signal, and so it's gonna lose the high frequency.
Mm-hmm. Okay, but more complex networks, like message passing.
I mean,
like
in theory, you can always, in theory, you can always think about, you know, some methods that in theory can keep these signals, keep the high frequency, yes. But most methods have been shown to basically mainly perform smoothing and so, you know, not use high frequencies. Of course, you know, in principle, there's been other methods, but methods that are used most commonly in practice, they do not do that.
Okay. Then thank you.
I would like to add.
Okay,
I'd like to add some points here.
Addition by Dom and Michael. Is it okay if we leave your question for later? All right, Dom.
Yeah, just quickly would like to say that MPNNs are not necessarily better than GCNs at preserving information. The only difference is that they can also they can also use edge features and themselves, but most of the time they use mean aggregation, and so they actually lose information. They actually also suffer from over smoothing, although a bit less than GNNs. So one thing I would like to add is you work in the field of molecules, and for molecules, it is one of the major bottlenecks of most methods of graph neural networks that they over smooth information. And definitely you will not be able to use this kind of diffusion method to find missing atoms. Like if you have a molecular graph and you want to find missing atoms, you cannot just say like, if you have a carbon and an oxygen, the average between them is a nitrogen. Like you don't have a smooth function. You need to use other kind of methods that are probably more chemistry based to be able to generate the missing features in molecules. But for most of the cases where Emanuele is working, for example, social networks and knowledge graphs, and this kind of networks, then information is known to be very smooth in these cases. So having this kind of algorithm can work very well, and is shown actually to work very well, just because the type of networks on which he's working are networks with smooth information.
Yeah, makes sense. Thanks.
All right.
Yeah, thanks, Tom. That was very clear. Okay, so yeah, this just was a quick recap of what exactly is going on. So again, as I was saying, this is kind of almost like a pre-processing step. So this FP is our feature propagation. We run the previous algorithm to reconstruct the missing features, even though, as again, we do not care that much about the reconstruction itself. And then we feed these reconstructed features into a GNN to make the final classification. And again, I would like to emphasize that the main, I think the main benefit of this approach is that of being extremely simple. So it's basically 3 lines of pseudocode and also super scalable. And it works super well. So we're gonna see all this in the experiments in a second. Before that, this is just to kind of illustrate a little bit what I was saying before. So feature propagation is acting as a low-pass filter, which means is only smoothing the signals, only keeping the low frequencies. So this is a plot showing that. So in the x-axis, we have the frequencies of basically the Fourier transform of the graph signal, and low frequencies represent smooth kind of signal, and high frequencies represent kind of non-smooth signals. And the regional feature is kind of all over the place, so it's not really smooth. So it's the red one. If you instead look at the reconstructed features, in the extreme case, let's take the extreme case of 99% feature missing, then the reconstructed feature is super smooth. So all the high coefficients are mainly in the low part of the spectrum. So the low frequencies, apart from like a small spike at the end. But if you look at the mass of these coefficients, is basically almost all in the low frequencies, meaning it's very smooth. And this is again is similar to what most common GNNs are doing, and so they work well when used in conjunction. Yeah, as slides to basically comment on similarities and differences from label propagation, which I also saw as a question. So I think this can answer that question. So they are clearly algorithmically very similar, but the idea of label propagation is that of propagate class labels, which are usually discrete. And whereas in feature propagation, usually we deal with features which are continuous. This just results in some changes in the derivation and in the diffusion matrix. In label propagation, you make a prediction, which is obtained directly by propagating labels. Whereas in feature propagation, we propagate features, and then we use a GNN on top to make the final prediction. And finally, label propagation is feature agnostic. So it is not able to kind of use features if you have them. Whereas feature propagation, by combining with a GNN, it's able to use features in an effective way. And we saw that even if you have a low % of feature, it's worth using them because you can outperform label propagation, which doesn't use features. And so label propagation is an effective solution for the missing features problem. So enough talking. Let's look at some experiments. And so what is this plot showing? So this plot is showing the accuracy as a function of the rate of missing features. So on the x-axis, we have how many features are missing, going from 0, so we have all features, to 99% feature missing. So only 1% of features are available. We have all the baselines that I showed before, so simple imputation methods, 0, random, global mean over the whole graph, neighbors mean, where you take the mean only of your neighbors, as well as label propagation, which remember is does not use the features. So it's just a straight line because it doesn't matter how many features are missing. And the 2 previous works for this problem. And our method is shown in yellow. And I think here, I mean, the performance is quite, the gap is quite striking, in the sense that it doesn't really matter up to 40, 50% of missing features. They all kind of work similarly well. But as you have more missing features, then the gap opens up pretty big, especially in the extreme case of 99% missing features. Feature propagation combined with a 2-layer GCN It's the only method, and all the other methods are combined, basically are identical models. It's the only method that outperforms label propagation and kind of by a wide margin. Clearly, in 2022, nobody trusts Cora anymore, and neither do I. So we actually evaluated on a lot more data sets. So here I showed the other data sets. So we have also the Amazon photo and computer data sets, OGBN archive. And, you know, the pattern is kind of the same everywhere. In some data sets, the gap is smaller. In some other, the gap is bigger. Here, in some data sets, it also seems very small just because the other methods kind of decrease so dramatically that to keep everybody in place, then the gap decreases. But our method is always basically very, very robust. So if we zoom in a little bit, and we look at the performance, only when you have 1% of features, so 99% missing, and we compare our method to label propagation and the two previous methods, you see that the gap is kind of huge compared to the previous methods, which, as I was saying, they cannot withstand high rates of missing features. But we also do always better than label propagation. Because you could say maybe, you know, you have only 1% of the features, just throw away the features and do not even use them, right? Just use the labels and do label propagation. However, we show that there is an advantage in using the feature. And also I would like to emphasize that these are not these are not results obtained by like some crazy tuning. Actually, we basically did not do any tuning at all. And the method is super kind of resilient. I mean, the method is just pre-processing, so it doesn't have any hyperparameter or anything. Then there's a simple two-layer GCN, and did not do any tuning. The standard hyperparameters, which are known to work fairly well on these data sets. Label propagation did tuning on like the kind of alpha parameter with kind of 10 reasonable choices. So these are kind of results I trust a lot. And it's basically always performing better than label propagation on this extreme case. If we just look at feature propagation, I was now interested in saying, okay, look, how much do we lose compared to when we have all features? When we have, you know, 50%, 90%, 99% missing features. So it turns out that on average in all data sets, if you have 90% of missing features, you only lose 2.5% of relative accuracy, which arguably is kind of little. And if you throw away 99% of your features, so basically you're left with very, very little, even at that point, you only are losing 4.10% of relative accuracy. So I was actually quite impressed by these results, because you're basically throwing away all your features and still you lose very little, but you still do better than not using features at all. So I think that's kind of quite interesting. As I was saying, we're also interested in scalability. So here we're showing a plot of how long it takes to do using feature propagation, both the reconstruction part plus the GNN training, compared to PA, GNN, and GCNMF, so the other two kind of previous methods. And FP is kind of 3 times faster in the end-to-end training. GCNMF doesn't even run on OGBN archive because it goes out of memory. But I think what is even more interesting is that the reconstruction part, so all the time that you see here is basically all of it is only the training of the GCN, which we can't really do much to kind of alleviate because that's just the GNN training. But the reconstruction step is kind of super fast. So if you take OGBN products, 2.5 million nodes, 120 million edges, takes 10 seconds on one GPU. We were able to scale this to an internal data sets with basically almost 800 million nodes and around 10 billion edges. And it took 2 hours to do 15 steps of feature propagation, which was enough for convergence on a single machine, a big one, on CPU. And I now implemented this in BigQuery, which is kind of the Google SQL, distributed SQL language. And this whole thing runs in 45 minutes. And basically there are no limits to scalability. So you can, there are going to be some limits, but not like you can still scale it a lot. So we are very excited. Twitter for actual applications of this method because it's super scalable, super fast, and quite simple to use. So yeah, okay, so very interesting slide because this touches upon many of the previous discussions that we had. So as I was saying, we made this homophilia assumption, and this is an assumption, right? So it's not gonna be true in all cases. And we were interested in seeing when this assumption does not hold. And clearly it does not hold in heterophilic data. And so we wanted to see how feature propagation was performing in heterophilic data. So we took a synthetic data set from a previous paper where there are like a bunch of graphs where the graph is the same, but you change the edges so that you can control the homophily level, going from 0 to 0.9. And if you clearly, when the homophily is high, even for a model working on the on all features, the problem is much easier. And in our case, using feature propagation, so the yellow line, if the homophily is very high, we can perform basically as well as observing all features, even if 99% of the features are missing. So this is kind of the scenario we were seeing before on the benchmarks. However, as you start decreasing the homophily, as you go to 0, basically there is a huge gap opening up, right? So if there is 0 homophily, our method does not perform much better than just filling the missing features with 0, which is interesting. And I think this kind of opens up a very interesting, direction, follow-up direction, which is, how do we make this work on heterophilic data, which is something we're actually currently looking at. So as future direction on top of this heterophilic data that I just mentioned, another one is to do something which is end-to-end learnable. So as I was mentioning, feature propagation is not learnable. It can be thought as a pre-processing step. I mentioned already, if you want to optimize for a given task, you may want to do a diffusion which is learnable. You would have to give up some scalability, of course, and also some simplicity, but you would probably gain on the performance. And another interesting direction could be to make use of channel mixing, which basically means that the method right now diffuses each feature channel independently, but you could think of many cases where one feature channel is informative for the reconstruction of another feature channel. So using kind of correlations across channels can be helpful in the reconstructions, and is something that is currently not done. So a couple of future directions, and we now get to the conclusion. So, if you remember 5 things about today, what you should remember. So I think, first of all, the missing node features is a very widespread problem in the real world, even though it's barely been touched by the research literature, but is what happens, in most cases in the real world. We have an approach which is theoretically motivated, and we showed that it works, and it's robust especially works well with high rates of missing features. So having more than 98% of missing features up to 99%, we still perform very, very well. But what I'm most excited about is that it's actually super scalable, super fast, and super simple to work with, which makes it very suitable for industrial applications. We also showed and discussed about some limitations. In particular, we have this homophily assumption, which kind of limits its applicability to graphs that are, they are slightly, or they are quite homophilous, which is the case for most benchmarks in graph neural networks, research. Even though now there is a rising interest, which I think is very well justified, on heterophilic data and creating new heterophilic data sets. So with this, I would like to conclude, and if we have time, take any more questions that you may have.
We absolutely do have time, and only after we say thank you very much, but let's keep the questions coming. Johannes.
Hey, thanks for your presentation. I just have a brief comment and maybe a silly question, but the comment I have is that the Dirichlet energy is closely linked to the eigenvectors of the Laplacian matrix. I mean, the eigenvector corresponding to the smallest eigenvalue minimizes the Dirichlet energy. And this is the smoothest eigenvector available on the graph. And so if you define heterophily as a situation in which features should exhibit a high frequency on the graph, somehow a simple route to go would be to maximize the Dirichlet energy, which you might be able to achieve simply by using the eigenvectors corresponding to the largest eigenvalues. And the eigenvectors in between also allow you to access all kinds of other Dirichlet energies. You don't necessarily have to aim for an extreme. This is the comment, and maybe the silly question that I have is, why did you call this work the unreasonable effectiveness of propagation? Like, what would you say makes this unreasonable?
Yeah, it's the unreasonable stands for the fact that it's super simple, and we were not expecting such a simple method to work as well. And the title is actually taken from work, kind of a very famous work of I think it's the reasonable effectiveness of mathematics in natural sciences, which was a very famous kind of old work, and there's been also reused by Andrew Karpathy in one of his blog posts, the reasonable effectiveness of recurrent neural networks. So it's kind of it's been used before, so it was not like we didn't make it up, but it's mainly to state down how surprised we were when we saw the results.
Cool. Yeah.
And about your comment, I think it makes sense. I think the main issue is that I think homophily is well defined, means kind of low frequencies. Heterophily, heterophily, I'm still, I've been trying to read all the papers about heterophily. I still don't know what heterophily is, because it looks like people are saying heterophily is anything which is not homophily, and then it's very hard to characterize. So it can be, if it, then is, if you say only the high frequency eigenvector, then is one specific case, right? But you don't cover all the other cases. And so I think it's very hard to just one simple formula like that to optimize it and then to hope to kind of deal with all cases of heterophily. But I agree that if you define heterophily as having like only high frequency eigenvectors, then you can certainly do it like that. However, I think heterophily is much more complex than that. And I don't know, I wouldn't even know I haven't really found a convincing characterization yet, to be honest.
I also think this is missing. I mean, you can have heterophily of features, of labels, and of the graph structure. And at the moment, people are not specific what kind of heterophily they're referring to. You're right.
Well, here we would be talking about features, right?
Yeah, features, which kind of tends to go, I mean, if you're working with a task, then you also want the task. I mean, it's a bit complicated. I think features and labels tend to come, it's hard to look at them independently. But yeah, mainly features.
Yeah, okay. But we have another very interesting point in the chat. What happens if you, in your experiment where you show that you only lose 4% accuracy when having 1% of the features, what's the accuracy of when using no features at all there?
Yeah, so no features. So the question with no features is, what do you do when you have no features?
You can only use the graph structure.
So I ran these experiments, right? So if you set, so no feature, you have no features, right? So you can't use feature propagation, okay? What you can do, maybe you have an all zero feature matrix. It's gonna be a random classification, right? Or like, I mean, it's gonna be a very poor result. So I tried that and it's kind of terrible. What actually performs slightly well is if you have random features, because in that case, it's like giving a random signature to each node. And there's been a few papers showing that that kind of works well, because if you use a GNN on top of random features, then the node kind of encode the node features and node embeddings encode the graph structure. However, it was always kind of underperforming label propagation in my experiments. And yeah, I did not show that here because all methods were kind of plummeting and kind of destroying the plot, or we're making the plot unreadable. But kind of, I think label propagation is the real baseline for no features in this case.
Then maybe also just a quick understanding question. Do you mask out each feature independently or mask out all the features of a node?
Yeah, so when we're dealing with vector valued features, which as I was saying, we never show in this presentation, but is what we do. Each feature is independently. So we have a mask. So you have this mask, which is the same size of the feature matrix. And then each entry in the matrix can be either present or missing. The case where either you observe everything for a node or nothing is a subset of this more general case, which also is kind of quite present in the real world. So we also tried with that scenario, but it was basically performing identical to the current results, which if you think about the method makes sense because we are diffusing each channel independently.
Yeah.
So it doesn't make a difference.
Okay. Another question. Would you consider adding some randomness to the features after the feature propagation to limit the over-smoothing? I don't see how that would help. Do you have anything to say about that?
So I think I guess the point is, if the output of feature propagation is overly smooth, then it may be hard for a GNN to do anything. So I think in most cases it seems not to happen. If it could happen, I think what would make more sense would maybe just to concatenate like a random vector to the feature propagated vector, to the reconstructed features,
But how
to have this
help?
signature.
How can that help?
Because if you think about the extreme case where for some reason feature propagation outputs the same vector for all nodes, then you can basically, I don't think it can happen, exactly like this. Maybe in some super extreme case.
Well, you wouldn't end up outputting the same vector for each node, right? You would end up outputting, like if you smooth infinitely, then you end up outputting, yeah, if no, you're right. Okay, it makes sense. Yeah, got it.
So then basically at that point, the model cannot distinguish the nodes anymore, right? So having a random signature, a random vector may help, but I would, more like concatenate it maybe than add it. But I think I don't know how often this would help, but it's something that could be tried for sure.
Okay, then let's wait for any other points while I say thank you for the nice answers to all of our questions. And I really enjoyed how many questions and super good questions we had in the chat today. And also the people who spoke up. Thanks. And thank you for the awesome presentation.
Well, thank you. Yeah, the questions I think were all very, very interesting, very insightful discussion.
Thank you for the great presentation. I'm looking forward to something more flexible and learnable, as you said, to be able to, instead of just propagating based on smoothness, propagate different kind of features based on different level of smoothness. So, but that's a very interesting work, and like I really like the title also because the results are way better than expected.
Yeah, but I agree. I mean, there is a lot more work to do. This was more like a first attempt to solve this problem, but there is still, you know, a lot of margin for improvement.
Yeah, but I think the title is good in any case. We need strong titles to sell our work, and this is actually catchy. All right, but then let me do the unthinkable thing that I do every time of putting the author in a tough spot with asking, do you have some parting wisdom for us as final words?
Some
last wisdom, some parting wisdom. Like what do you think will be the next thing here? Or maybe even what's the solution to graph neural networks?
Yeah, I think in general, I would like, I mean, which probably you can see from this work, I would suggest, I mean, just very personal opinion, but I think there is a very big trend of going towards always more and more complexity, which tends to help with publishing in conferences, but I think it doesn't always help with the research and also with the adoption of your research.
Did you get reviews in iClear that were like, yeah, this is just too simple, basically?
Yeah, of course. I mean, we did, but I was not surprised. I was expecting.
Okay.
So I mean, in general, I have a track record of papers that are deemed too simple, but in the end, like they are always the ones that are kind of get the most attention, the most adoption, because it's what, you know, something that can be understood and used more easily by people. So by now, my work is mainly driven by kind of getting interest and adoption by the community. So I'm also working on, hopefully the code for this work will be released soon. I'm just waiting for some internal sign off, but I'm trying to make it, you know, as easy as possible for people to use this. And I think when something is simple, it's kind of much easier to build on it, to understand it. And I don't like kind of unnecessary complexity, which I think is an unwanted artifact of the not perfect incentive system of the current, you know, ML research landscape. So I would urge people to kind of try and actually, you know, think about whether they actually need that more complex bit or something of you know, things can be done more simply and achieve the same end result.
All right, I'm absolutely convinced that we couldn't have any better parting words. So I think it's the perfect time to call the day for today. And let's have a last thanks for Ema, and then see you all next week, I hope.
Thanks a lot again, Hannes and Dom, for having me. It was a pleasure.
Okay, those were perfect parting words from Emanuele. And let's remember that we don't want complicated methods, we want methods that work. And we'll hopefully have many other such methods presented here in the reading group. So make sure you don't miss those and join the reading group sessions yourself with all the information in the description below. Slack channel with weekly updates, email updates each week, and also our social media.